Hello again, YouTube. The last time we left it, we created our little API of two functions, basically an initialization function and a transmit function. And we had taken being passed a character string from our application code, and our implementation just basically copied those received characters into a circular buffer. And I kind of went over the circular buffer and how that worked. So now we have to convert these ASCII characters. We've said a valid ASCII character is, we're going from A to Z. We're not doing the numbers 0 to 9 or the digits 0 to 9, and we're not doing some of the punctuation marks for the minute. We're just A to Z, concentrate on that. So now we've got to translate that A to Z into the dots and dashes of the Morse code. So if we look at Wikipedia, their entry for the Morse code, there's this representation of the Morse code. Now, that's not the only valid representation. In one of my first introductories to Morse code, I had this binary tree. So that binary tree is actually also in this article further on down. So I've got that in another tab. So we've got two representations here. We've got a binary tree. This is called a binary tree because, well, it's obvious. Each node in the tree has one parent. So A's parent is E. E's parent is the root node. This would be called the root node at the very top of the tree. So A's parent E, E's parent root node. A has two children. And in this representation of the Morse code, the sensible things to call them are dot and dash. So A's child dot is R, A's child dash is W. And every node in this binary tree has that structure. Some nodes, like this slash, has no children, so it would be described as a leaf node. And some nodes, like X here, has only one child. But generally, the node has the ability to have two children, so it's a binary tree. Now, this is a very simple representation of a simple problem. If you were trying to represent the game of chess, and your root node was the starting position of a chessboard with everything lined up in the starting position, you might have, I don't know how many possible moves there are for the first move. There could be 10 moves. So instead of having two children, there could be 10 children coming out of this a root node, each child representing a valid move in the chessboard. And each then position would have children fanning out from it. So that's just a representation of the problem. The reason I'm getting into this is because we have to convert. Our problem now is that we have to convert an ASCII character between A and Z into the dots and dashes of Morse code. That's our problem. And one of the main things in software engineering is deciding upon the data structure which best suits a problem space. And if we pick the wrong data structure to represent our problem space, we will make our solution much more difficult. So it's sometimes things look very simple because the data structure that's been selected actually suits that problem. So I've got two data structures here, two representations of the same data, and I'm going to encode using a binary tree because it will make the actual solution to the problem much more simple. And to explain that, if we're transmitting a character, so if we're transmitting a J, for example, if it's very easy in this implementation, if we've got this A to Z is going to be an array of the characters. So when we transmit J, we just select our array element at the J index. Sorry, can't be doing that. And it's just dot dash dash dash. So we just look it up straight. We've got a straight index into that, and we can very quickly see it's dot dash dash dash. Now in this the alternative representation. Our J is down here. Now we could actually have again we could have an index into an array of characters, and our J index points at this. Sorry, I shouldn't have done that. This character J. And now to find what the actual Morse code is for J, we have to traverse back up our binary tree. So we have to go to the parent of J, which is W, the parent of W, which is A, parent of A, which is E, and then the parent of E, which is the root node. Having got to the top, we have to go straight back down again to get the Morse code. So J is dot dash dash dash. Now that is slightly more convoluted than just looking this J up and going dot dash dash dash. So you would think that this representation of Morse code is much more easy to code than this binary tree. The problem is when you take into account our API at the minute is just two simple functions, initialization function and a transmit function. But this Morse is a communications protocol mechanism. So if there's a transmitter, somebody has to receive. So when we come to receive the Morse code, then that's a different problem. So if we give the example of, we've just given the example of transmitting a J character. If we receive dot dash 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 and then the end of character pause happens, or the end of character break in transmission, that timing, then we know we've received a dot dash dash dash. But what is a dot dash dash dash? And in this implementation, we would have to go through each one of these characters one at a time and search for what is a dot dash dash dash. And we'd get down to J and go, that's dot dash dash dash, we've received a J. We've actually created a search problem. And there's ways of optimizing search problems, but every time we receive a string of Morse elements, we have to then search through this to try and find out what it is we've actually received. If we do the same reception using a binary tree, if we're in the default state, in the idle state, we're at this root node and we receive a dot, then we move to this node. If we receive a dash, we move to this node. We receive another dash, we move to this node, and then finally we receive a third dash, we move to that node. And now when we time out, we just know we've received a J. We don't have to search through a binary tree, we don't have to search through anything. We've actually just, during the reception, we have traversed through the tree, and when we get a timeout, we're actually pointing at the letter we've received. So reception is much easier in this binary tree implementation. So if you were to weigh the two up, the computational cost of this implementation, it's very cheap for transmission, very expensive for reception, relatively speaking. We're looking at we're working, the Cinnamon Bun is running at 60 megahertz, so it's not going to take much to actually find every time, but this is much more succinct. It's be much more elegant solution to the problem when we just traverse down. And so reception is so much easier in this, and transmission is just inconvenient in the fact that you have to traverse backwards up our binary tree. So I'm going to implement a binary tree, and that implementation would go into Morse.h is our API. It's a public API sort of thing, which our application code in main.c picks up. So the application code doesn't need to know how we were implementing the solution, so this would not go into that file. So we're just going to create this with a structure, and we're going to create a C structure for a character. Now that's not a C char, but rather it's I could call it a node instead of a character, but it's actually representing a character and a node. 6 of one, half a dozen of the other. But each one of these represents a character. So we actually have to keep a track of our C char. We'll just call it CH. In addition, this A node has a parent and 2 children, dot and dash. So those 3 other elements are going to be pointers into another one of these structures. Sorry. And that's our node. If you can spell. So that's each one of our nodes, which represents a character, is represented by this. It represents a character and has a parent and 2 children, dot and dash. Now the actual data structure, the alphabet, is going to be an array of these structures, and we want to hold on to, I'll just use the ASCII values. So we're sorry. So we're actually implementing this for A to Z. So whatever the ASCII for Z is minus the ASCII for A is going to give us our 26 characters. I want to add on 1 because we want to have a node for the root as well. And we'll call that index 0 into our array will be the root node. But I'll add this just to be explicitly say that we're adding on 1 for the root node. The other thing I'm going to do is define a macro for the index. Now, our index into the array is always going to be 0, 1, 2, 3, up to the size of the array minus 1. So it's, in this case, we've got 26 letters plus the root node is 27. So the index of the array is from 0 to 26. But 0 to 26 doesn't mean a lot when we're talking about an alphabet. So I'm going to convert, I'm just going to write a macro that converts an ASCII character into an index in the array, and that would be given by whatever the value is minus the ASCII for A. But we'd have to add on 1 again for the root node. So that when we pass in, when we try and get the index of the letter A minus A is 0, plus 1 is 1. B minus A is 1, plus 1 is 2. So this macro is just going to, given an ASCII character, is going to give us the index we're looking for. And given all that, we're going to initialize. We're going to do 2 stages of initialization. Now, I want for the first one to actually initialize things to all the pointers to null, just to make sure that they're initialized to a value. So we'll actually loop over the ASCII. So from A to Z, we're going to increment over that. And for a start, we want to say that our alphabet, and now we use our index into loop. So that's the ASCII value, and sorry, is equal to and that's just equal to the ASCII we've passed in the loop counter. So the character that this node represents is given by the loop counter. The only other thing we have to initialize is the parent and dot and dash the two children. Dot and dash the two children. Stupid names. So there we are. We have an error because null is in standard def. I think. Yeah. Just as an aside here, that this code is fine because it's ASCII 16 C compiler. Some C compilers, null is defined as a pointer to void. And that's at address of 0. Something like that. So null is a pointer to void. So sometimes you'll get a C compiler that will complain that you're actually setting a pointer to a character or structure character, assigning that a pointer to a void. Now that's an implicit type, a cast operation, which is usually allowed, but sometimes a compiler will warn you that you're actually implicitly converting from a pointer to a void to a pointer to a structure character. So if the compiler complained about that, then you'd actually put in an explicit cast operation just to clear that warning. This, like I say, the ASCII 16 compiler doesn't have that issue. So, well, it's a feature. It's not an issue really. It's just it's I suppose you could call it good practice that the compiler warns you that you're converting from one type to another type, and it will always do that. But generally, for a pointer to null, the void star, the compiler's happy with that. Some of them aren't. This one is. Just as a warning, I mean, it just depends on the compiler. So, having done that, we've initialized it, initialized things. But the only thing we haven't initialized here is we haven't initialized for index 0 is our root node, and it doesn't represent a character at all. So we'll set its character to be 0. And now, having done that first stage of the initialization, I call that the first stage, we want to do the second stage. And that second stage is to go through each one of these letters, nodes, and set up the pointers, so that we initialize the actual structure of our binary tree. So our 0 is our root node. I'll just explicitly say that here. So it has no parent, so we can just leave that as it is, null. Both the dot and the dash are pointers into this alphabet, so they point to another structure, and they point to, I think it's E and T. But we're going to check that. Oops. So the dot, the child of the child of the root node, I was right. The child of the root node on a dot is E. A dash is T. And that's the way we build up this tree structure. And there's an error. I've got too many square brackets, not enough parentheses. So that's our root node. Now we have to go through every letter, which is every node of this tree structure, and initialize it. So we'll go through them in alphabetical order, I suppose, is the handy way to do it. So for A, and this is how this index becomes, we know A is the index 1. So I could put 1 here. But actually putting the code index, using this macro in this way, it becomes very simple to see. The code becomes more legible. That's all there is to it. And the most important thing about code is human readability, probably, because yeah, if the computer can execute it, that's one thing. The compiler's happy with it, that's one thing. But if you can't read it when you come back to maintain it, then you've got a kind of a problem. So A, again, it's another pointer into this alphabet structure. It's a pointer to another one of these structures, as are both the dot and the dash. So A is here. A's parent is E, and its children are R and W. So its parent is E, children R and W. And that's how we code this. So we go through every letter. And to save you watching me typing, you're not going to learn much from watching me typing. I've previously typed it. And that's the tree structure. So we go through initializing each of these elements. So A, B, you can see B has no children, it just has a parent. So B's there. It actually has two children in this, a 6 and equal signs, but because we're not implementing those in code at the minute, B has no children. So for every letter in the alphabet, which is every node in our tree, we fill out and initialize the data structure. And I should explicitly say again, so the parent of T is the root node, index 0. And as you can see, like I could have coded this as, and the actual macro, because we've implemented this index as a macro, the compiler will just replace this with 1. The index of A is 1. But it's much more easy for me to read this and say, well, the parent of A is E, and the dot and dash are R and W, and that's very easily, as opposed to seeing a 1, and this would be, or I'd have to get out my slide rule to work out what the index R is. Well, it's not a slide rule, but you know what I mean. It's much more readable and maintainable as a result. So I think that's kind of like a time limit. I'm getting to a bit long, so I'll leave it for there for the minute, and next time we'll actually use this structure and start transmitting again, and hopefully be transmitting strings. Thanks a million for watching.